Hi, in this video we're going to talk about generalized coordinates. So the beauty of the Lagrangian method is you don't need to know about the forces. It's based on energy, kinetic energy, potential energy. And your coordinate systems you can have don't need to have units of length. You can have units of energy or units of momentum. So we'll talk about generalized coordinates. We'll talk about number of degrees of freedom, generalized momentum. We'll talk about constraints and equations of constraints. We'll do at least one example problem where we have a constraint, and then next time we'll do one or two more example problems, and we'll talk about Lagrange multipliers next time. So that's where we're going. Okay, so in the Lagrangian mechanics, the coordinate systems we use don't have to be orthogonal. They don't have to be the orthogonal Cartesian coordinates. Coordinates in general are not orthogonal, and in fact they don't have units of length or angles. Don't have dimensions of length. Okay. So what generalized coordinates are, the definition, if you will, is that it's the term used to denote the coordinates used to completely describe the system. So the number of generalized coordinates that we need, and we call them generalized because they are not the usual orthogonal Cartesian coordinates. The number of coordinates, generalized coordinates, needed is equal to the number of degrees of freedom for the system. It's equal to the number of degrees of freedom. So what it boils down to, it's the number of ways, the number of ways that the system can have energy independent of any other way. So let's talk about the sphere through three-dimensional space. How many degrees of freedom does it have? So you have your sphere, the center of mass. You need three positions to describe where the center of mass is. So three coordinates. To locate the center of mass. But then you have the orientation of your sphere too. So if you mark a couple spots on it, how is it orientated in space? On Earth, which is fairly spherical, to locate a point on the surface, you need a latitude and longitude. So we need two coordinates to describe the orientation of the sphere. So thus you'd have 5 degrees of freedom. So we need 5 different coordinates to specify this sphere moving through space. Now, we can put constraints on the system. And what a constraint does is reduce the number of degrees of freedom. So constraints on the system reduce the number of degrees of freedom. So for example, if you, for the sphere, so if you have a sphere constrained to move on a flat tabletop, well then, on the flat surface of the table, you need 2 degrees, you need 2 coordinates to specify where the center of mass of the sphere is. So you need 2 coordinates for center of mass instead of 3 like you would have if it could move in the up and down direction too. And then you still have 2 coordinates for orientation. So now you have 4 degrees of freedom. So by confining it to the tabletop, you've removed one of the degrees of freedom. So we'd need 4 generalized coordinates. So again, for generalized coordinates, we don't label them X, Y, and Z because they're usually not length, or in general not length. We use Q1, Q2, Q3, up to Qn. So you write your Lagrangian in terms of these Q1, say Q1 dot, Q2, Q2 dot, up to Qn, Qn dot. And then all these might be functions of time too, so. Okay. Okay, let's talk quickly about generalized momentum. Momenta. Notice that, let's say we have, in our Cartesian coordinate system, we have our Lagrangian, we write like this, equals 1/2 m x dot squared, that's the kinetic energy, minus some potential energy. Okay. Now, notice that if I take the derivative of L with respect to x dot, what do I get? It only acts on this very first term here, and I get what we know as linear momentum. So in fact, we're going to define P sub q as the generalized momentum. It doesn't mean that it has the same momentum. It doesn't mean it has the same units as linear momentum, as you'll see in a little bit here. So then, if we take dl dq dot, that is equal to PQ. So that's our generalized momentum. Let's look at a quick example for that. Let's say we have a particle in a central field. It means it feels a force towards the center. Here's our particle, mass m. Here's the center. This is our origin. This distance, that vector is r. Here's horizontal. That's theta. So let's say that the potential energy for this depends on how far it is from the center. Let's just say it's a function of r, negative, I'm going to call it mgr. Okay. So what would be, so this thing can move all over the place. It obviously depends on two coordinates. In this case, r, how far it is from the origin, and theta, its orientation with respect to some axis, what I'm calling the x-axis. If you write down v squared, it's going to be r dot squared, and this is in polar coordinates, plus this is an arc length there, r theta dot squared, that would be the velocity squared in polar coordinates. 2 degrees of freedom. So if you want to, I'm going to call Q1 R, Q2 theta. My two generalized coordinates. If I find the momentum for R, it's equal to dl dr dot. So what is, we guess we didn't write L. L is equal to 1/2 m r dot squared plus r theta dot squared. That's the kinetic energy minus the potential energy. So we take the partial of L with respect to r dot. What do we get? We get m r dot. That's a linear momentum in the r hat direction. And then we have p theta would be dl d theta dot. And I mean, it looks like you're going to get m r squared theta dot. So this is a linear momentum, what we know as a linear momentum. And this is an angular momentum. Both are generalized momenta. Okay, notice that if I have P sub q, which is dl dq dot, if I take the derivative with respect to time, that's p q dot. Okay. Now, if we write our Lagrange equation with general coordinates instead of x or y here, we write, so our Lagrangian is q dot t. Then our Lagrange equation becomes this. And we see that this is actually BQ dot. So since this is 0, we can say so we get our generalized momentum is dl dq dot, and the time derivative of that momentum is okay. So I have a couple more things to say about generalized momentum and constraints. So first of all, if the time derivative of p of q, let me write that over, time derivative of p of q, which we said is this, if that's equal to 0, what does that imply? That implies p of q is a constant, right? And if that's so, we call the coordinate q an ignorable coordinate. Meaning it's not going to be very interesting, right? It just means for that coordinate q, momentum is a constant, so there's no force, right? Because that just means p double dot q is 0. So that's what an ignorable coordinate is. And a couple more things about constraints. Back to constraints briefly. We said that a constraint reduces to the number of degrees of freedom, but you can write constraints in two ways. If you can write the constraint as a function of, let's say, x, y, z, t, minus some constant equals 0, we call this a holonomic constraint. So constraints that cannot be written in this fashion are called non-holonomic. Non-holonomic constraints. Cannot be written in this form. Okay. As an example, if particle constrained to the surface of a sphere. So here's an example, particle so we have our particle can only move on the surface. That means its x, y, and z coordinates are such that they equal, the square of them all equal r squared, the radius of the sphere. So we can write that as this. So this is a holonomic. But let's say we have a particle and it has to be within a volume of a sphere. Particle constrained to volume of a sphere. So it has to remain in the volume. Then we would say x squared plus y squared plus z squared is less than r squared. We cannot write this like this. So this is a non-holonomic. Constraint. And we'll talk about holonomic and non-holonomic constraints some more in a little bit. So here is a little summary now. We know that if we have n degrees of freedom for a system, we're going to have n generalized coordinates. We're going to have a Lagrangian written in terms of these coordinates. And we're going to have n Lagrange equations. dl dq1 minus and that the generalized momentum is that, and the time derivative is and that if this is 0, if the time derivative of the generalized momentum is 0, then that q is ignorable. It's called an ignorable coordinate. So let's do an example. Let's do what I call the yo-yo example. So we have some support up here. This could be a finger that doesn't move or something. We have attached to it a string, a very light string, and then there's this cylindrical yo-yo that has a radius, let's say a radius of a, and it's just falling under the influence of gravity. So first of all, I want to know how many degrees of freedom are there? I want to know, could you write the equation or any equations of constraint? Write the Lagrangian for this. So say any equation of constraint, Lagrangian, and then try to find the equation of motion. So I encourage you to pause the video right now and see if you can do this. Okay, so I want to figure out, I need to locate the center of mass of this thing as it moves down here. So I'm going to call the distance from up here to here, I'm going to call that y. So there's one coordinate. And then I need to designate the orientation of the disk. So maybe from this axis, so I need some theta. So it looks like I might have 2 degrees of freedom, because that's what I would need to locate the center of mass and the orientation of this as it moves down. But there is a relationship between theta and y, because as it rolls around 2 pi radians, I know 2 pi times a is the distance it moved down. So there's an equation of constraint between these two, and it's equal, let's say, y equals a times theta, so the distance that moves down is equal to the arc length that this vector here rotates around. So we have one equation of motion, and so instead of 2 degrees of freedom, we're going to have 1 degree, because this is a relationship between these two. It's going to get rid of one of those coordinates. So let's try to write, so we have 1 degree of freedom. That's our answer. So we got that. We got the equation of constraint. Let's try to write our Lagrangian. So the kinetic energy would, before we had this equation of constraint, we'd have a velocity in the y direction. Plus, so that'd be the center of mass moving down, but plus we have this rotational kinetic energy, so 1/2 the moment of inertia about the center of mass times theta dot squared, how fast it's rotating. So we have rotational kinetic energy, linear kinetic energy. By the way, for a disk, which I'm assuming the yo-yo is, it's 1/2 the mass of the disk times the radius squared. So that's the moment of inertia about the center of mass. Our potential energy would be a function of y, negative mg y. I assume it's 0 up here at the top. So we would have our Lagrangian plus 1/2 I center of mass theta dot squared minus mg, or plus mgy, because it's minus the potential. But now I have this relationship. I have theta equals, from the equation of constraint, y over a. So theta dot is y dot over a. So what I'm going to do is get rid of theta in the Lagrangian. So I'll write the Lagrangian 1/2 m y dot squared. And then 1/2, the I center of mass is this. So 1/2, let me write it over to the side. 1/2 I center of mass, but the center of mass is 1/2 ma squared. And then theta dot squared, but I'm going to say that's y dot squared over a squared. So I get 1/4 m y dot squared. And then my plus mgy. So now I have everything written as a function of y and y dot, my Lagrangian. And I can simplify it a little more, because 1/2 and 1/4 is 3/4 m y dot squared plus mgy. So there we go. So let's find the momentum, generalized momentum. That's going to be 3/2 m y dot, and then dl, well, let's take the derivative of that. And that is equal to then 3/2 m y double dot. And then we have dl dy is just mg. So here we go. Here's our equation of motion, which is dl dy minus d dt dl dy dot equals mg minus 3/2 my double dot is 0. So there we go. I have the acceleration in y direction. It'll be 2/3 g. So I would encourage you to do this problem without using Lagrangian mechanics. Use Newtonian mechanics, get the acceleration, and then use Lagrangian mechanics here and see what the difference is. See how easy it is with Lagrangian mechanics compared to Newtonian mechanics. Okay. So next time we'll do some more examples, and then we'll also talk about Lagrange multipliers in the next video.